We can use the basic shape of a functions graph along with different transformations to be able to quickly sketch the graph without having to worry about plotting a lot of points. So in this video, we're going to look at vertical shifts or translations, which is up and down, and also horizontal shifts or translations in a graph, which is left and right. So we're going to look at the formal definitions, and then we're going to talk about the easy way to remember how these different transformations are applied. So for vertical shifts or translations up and down, if a real number k is added to the right side of a function y equals f of x, the graph of the new function y equals f of x plus k is the graph of f vertically shifted up if k is greater than 0, or down if k is less than 0, and it's going to be k units. So that vertical shift up and down is going to be k units. So if we add 3, we're going to shift up 3 units. If we add -5 or subtract 5, then it's going to shift down 5 units. So our example, let's use the graph of f of x equals x squared to obtain the graph of f of x equals x squared minus 4. Well, the first thing we have to do is remember the basic shape of our graph x squared, and hopefully you have studied those a little bit and you know that the basic shape of x squared is a parabola with its vertex at 0. So this is going to be x squared. What we want to do is apply transformations to get x squared minus 4. Well, we have k added a -4, so that is going to be a vertical shift down of 4 units. So we're going to take our x squared graph and we're going to shift it down 1, 2, 3, 4 units. So notice that nothing on the graph changes except that all of the points have been shifted down 4 units. So the black graph would be x squared and the blue graph would be x squared minus 4. Just like we can have vertical shifts up and down, we also have horizontal shifts or translations to the left and right. If the argument x of a function f is replaced by x minus h, h being a real number, the graph of the new function y equals f of x minus h is the graph of f shifted horizontally left if h is less than 0, or right if h is greater than 0. Now, one of the things I want you to notice about this one is that when we were working with the vertical shifts, they made sense. If you add a number, you would expect the graph to shift up. And if you subtract a number, you would expect the graph to shift down. But the horizontal shifts are actually counterintuitive. They're backwards of what you would think makes sense. And it's because of the way that it's defined. Notice that this is x minus h, so the h has already been subtracted in this case. So that means that horizontal shifts are actually backwards of what you would expect. So keeping in mind that a vertical shift occurs when we add or subtract to the entire function, and it makes sense. Positive is up, negative is down. A horizontal shift or translation occurs when we are adding or subtracting to just the argument. So you'll notice in this example, the -4 was not just on x, it was on the entire graph. In this example, notice that the +2 is only on the x. It's inside the absolute value, so that means it's only on x. If it were outside the absolute value, then it would be a vertical shift. And the horizontal shifts are backwards. They're counterintuitive to what you would think. So if we have the graph of absolute value of x, which hopefully you have studied and you remember that that looks kind of like a V here with its point at 0, 0, then a shift of +2 on the x is going to be a horizontal shift, but remember, you would expect +2 to shift it to the right. It actually does the opposite, and it shifts it to the left 2 units. So the absolute value of x plus 2 would actually be a graph that looks more like this, because we are shifting 2 units to the left. Now, in addition to being able to shift up and down or left and right, we also will have scenarios where we will shift both up and down and left and right, and or left and right, left or right. So in this case, we have f of x is equal to x plus 3 squared minus 5. So notice we have two different transformations happening here. We have a plus 3 that is inside the parentheses, so it's only on the argument. And we have a minus 5 that is outside of the parentheses, so that's on the entire function. So first thing we need to do is identify what is the common graph, or the parent function, I like to think of it. And in this case, it's x squared. So we're going to start with that parabola with our vertex at 0, 0. And let's fix that a little bit. It got a little wonky on me here. And then we're going to apply two different transformations. The first transformation is going to be the minus 5. So the minus 5 tells me that we're going to shift down 5 units. So I'm going to take my graph here in black, and I'm going to shift it down 1, 2, 3, 4, 5 units. And there I have the graph of x squared minus 5. And now I need to apply the plus 3. So what kind of transformation is that going to do? Well, the plus 3 is on the argument. It's on x. So that tells me I'm going to go left or right. And because it's a plus 3, and remember, it's opposite of what makes sense, so it's going to go to the right, I'm sorry, to the left 3 units. And I'm going to quickly come in here and see if I can shift this little graph right here up just a little bit, because it's a little off from where we want it to be. There we go. That's a little bit better. Well, no, now we're a little too high. There we go. Let's try that. Okay, so now we're ready to shift it to the left 3 units. So we're going to shift 1, 2, 3 units to the left. And again, we're going to keep the same basic shape. We're just going to shift it a little to the left, or 3 units to the left. And so now we have the graph of x plus 3 squared minus 5.